So here's an instance where the history is so compelling that we have to follow it. So the image here is, of course, the Great Spiral in Andromeda. Over the course of the centuries, astronomers had classified stars and they'd found planetary nebulae, and they knew about gaseous nebulae like the Orion Nebula. And then there were these spiral nebulae, of which Andromeda is a spectacular example. This thing is almost 3 degrees across in the sky. Remember, the moon is a half a degree across, so this is huge, but very, very faint. You need a big telescope, and to get an image like this, lots of light collection and processing. But spectacular and beautiful though it is, it was not at all clear to anybody what it is, and what this comes down to is the question that has been hounding us throughout this class: how far? If you know how far, you can use the small angle approximation to figure out how big, but how far is it, this thing? How do you measure the distance? And this proved to be a big question in early days of the 20th century. So in 1920, in fact, there was a public debate conducted between two of the leading astronomers of the day, Harlow Shapley and Curtis. And Shapley made the argument was over the following question: these spiral nebulae, like Andromeda, are they gaseous nebulae within the Milky Way, or are they Kant's original island universes? Kant had this reasoning that these spiral nebulae should be worlds, universes on their own, just like the Milky Way, because there should be a hierarchy of structure, as I understand it. So Shapley, in fact, argued that there is no way. This was a scientific argument, and Shapley was arguing that these spiral nebulae are gas clouds in the Milky Way, and his arguments were basically this. If you take M31 to be 100 kiloparsec in radius, because that was the radius that Shapley had found for the radius of the Milky Way, and he knew one galaxy. He said, okay, if you're going to make this another galaxy, then it's probably going to be like the Milky Way. If you give Andromeda a radius of 100 kiloparsec, that puts it 2 megaparsec away, more than 6 million light years away. If Andromeda were to be that far, we'd already seen that there are stars embedded in these nebulae, and they had tracked, most interestingly, novae. So there were, presumably, we now know, white dwarfs with binary partners, and there were novae going on in these stars. And the luminosity of a nova is not really constant enough to make it a standard candle, but the maximum luminosity, the order of magnitude of luminosity of a nova is known. And what Shapley noted is that if you take M31 and put it 2 megaparsec away, then you would find that its novae must be much more luminous than those in the Milky Way. This is unlikely. It's much more reasonable to put it 100 kiloparsec away on the other side of the Milky Way, where it can safely reside. He also thought that there were measurements of the rate of rotation of another spiral, M101. And again, if you assume that M101 has the size of the Milky Way, then you find that it is rotating too fast to be bound. Curtis had reasonable arguments on the other side. His argument was that these spiral nebulae are indeed island universes far away and outside the Milky Way. And again, he was referring to scientific evidence. He was saying, let us assume that the novae in M31 are the same as the novae we find in the Milky Way. We know the average luminosity of a nova. This puts M31 at least 150 kiloparsec away. If you put M31 150 kiloparsec away, notice a lot closer, almost by a factor of 10 than Shapley did, then its size is about 7.5 kiloparsec, which is quite reasonable. This is about the size of Kapteyn's measurements for the Milky Way. Remember, Shapley's measurement of the 100 kiloparsec Milky Way had not yet been accepted. It has never been accepted. It was wrong by a factor of 2. And there was this alternative, small Milky Way. So it basically comes down to what is the size of the Milky Way will tell us whether Andromeda is in it or out of it. Also, he noted that we measure radial velocities for stars in these spirals, but we measure very little proper motion. This suggests that they're very far away, unless these objects are preferentially moving radially. Something has a large radial velocity, you expect it to have a large tangential velocity, remembering that the tangential velocity is related to proper motion by v equals V tangential is 4.74 times mu times d, you measure a large V and a very small mu, you conclude that you have a large d. This is how Curtis sought to reconcile these measurements. Both of them had valid arguments. Neither carried the day. All they did was illuminated the issue. The issue was actually resolved conclusively and beautifully by Hubble in 1923. So we have here, in fact, the plate on which Hubble made his discovery. So Hubble was investigating photographic plates taken of M31, the Andromeda Spiral Nebula. And in this region of M31, this is the region near the center, is what he was taking plates of. And he found a few novae. He was marking off novae because measuring, as we said, the luminosity of novae was one way to estimate the distance. How do you know that a star is a nova? Well, it's a nova if it appears as a star in today's plate, but was not there on the plate you took a week ago. So you compare new plates to old plates, and the new stars that have popped up are novae. And there's a date on when he took the measurement in October of 1923. And then he went back and he realized that one of the novae he had marked, the one in the upper right-hand corner, actually was present in older plates. And then was absent in yet older plates, but was present in... He had found a variable star. And this was a very exciting discovery because unlike novae, for which you only know the maximum luminosity, for variable stars, we have a period luminosity relationship. We can compute the luminosity of this star. Since we can measure its brightness, we can use that to find the distance. And Hubble was clearly excited. You can see that he vigorously crossed out the N and with a big exclamation mark marked on the plate, this is a variable. That's the VAR up there. He knew he was about to measure the size to Andromeda. He made the calculation, and the period luminosity relations showed him that Andromeda was 285 kiloparsec away. That is too big to fit even in Shapley's large 100 kiloparsec galaxy. Andromeda is a separate galaxy. Now, the distance measurement was wrong. We'll discuss that in a second. But you have to pause for a minute and appreciate the sort of Copernican magnitude of that VAR and why it was that Hubble was so excited. He had just realized that the universe is not one galaxy, but two, and of course, once you have two, presumably millions, and as we know today, hundreds of billions of galaxies. And so he had increased the size of the universe exponentially with this one variable star. A very exciting discovery. Following in its trail always gives me goosebumps. Just looking at that plate, I can imagine Hubble's excitement. So I said his distance was wrong, and this is a good exercise in following how creative and how exacting astronomers had to be to figure out this three-dimensional structure that we take for granted because we read it in books. So remember that the period luminosity relation was discovered by Henrietta Leavitt in Large Magellanic Cloud Cepheids. There are Cepheid, these are population 1 classical Cepheids in the Large Magellanic Cloud. Now, she did not know the distance to the Large Magellanic Cloud exactly. What she discovered was a period brightness relation, and she knew they were all about the same distance because they're all in the Magellanic Cloud. So she knew she found a period luminosity relation, but she couldn't calibrate it. She couldn't know exactly what luminosity corresponded to what period, only that twice the period corresponded to some factor times the luminosity. Now, Hertzsprung and Shapley both sequentially calibrated Leavitt's relationship using Cepheids in the solar neighborhood to which they knew the distance from parallax measurements. What they neglected was that these were Cepheids in the galactic plane, and extinction had made them appear dimmer by a factor of 4. So there was a 75% extinction to these Cepheids. They thought they were 4 times dimmer than they really were, and therefore their period luminosity relation was completely off. Now, Hubble was applying this measurement to a Cepheid in Andromeda, where he's looking outside the plane of the galaxy. His luminosity is off by a factor of 4 because you remember that our calculation of distance is proportional to the square root of the luminosity because brightness decays looks like L over D squared. The fact that he was a factor of 4 off in the luminosity of the Cepheid meant he was approximately a factor of 2 off in the distance. In fact, the factor he was off by was 2.7. Andromeda is farther than he measured by a factor of about 2.7. It's not. It's about 2.5 million light years away from here. Shapley, on the other hand, had been measuring the size of the Milky Way by measuring distances to globular cluster variables. But globular cluster variables are population 2. Those are W Virginis stars, not Cepheids. And at a given period, a W Virginis star is about 4 times less luminous than the Cepheid with the same period. Remember, we showed those two graphs of population 1 and population 2 Cepheids. And so Shapley unknowingly was actually using the right period luminosity relation. But remember, he was missing extinction, and so he overestimated the distances. And this led for a while to a great puzzle. Now that we had the distance to Andromeda, and we could therefore estimate its size by making a small angle approximation. You now know the distance. You have the angle, 3 degrees. Figure out the size of Andromeda and figure out soon the sizes of other galaxies. The Milky Way was larger than all the galaxies they saw. This didn't seem reasonable. And the diffuse extinction that Trumpler discovered in the 30s helped allay some of Shapley's, correct some of Shapley's errors, and the distinction between population 1 and population 2 Cepheids was not clear until 1952, when Bade realized that there were 2 populations of Cepheids and 2 different period luminosity relations. Now today, in the 90s, we managed to calibrate Cepheid periods directly from parallax measurements to distant Cepheids. Parallax measurements give us a correct distance. We know enough about extinction in the Milky Way to correct them, and you can use Cepheid variables to measure distances out to as large as 30 megaparsec. So that's 10 million light years. That's almost 100 million light years away. That we can use Cepheids as distance markers because we can still measure their periods. That's the distance record. Of course, it's still that gives you a luminosity. To compare to the brightness you see, you have to figure out something about extinction in the 100 million light years between you and the star. But we have a better understanding of extinction, at least in the Milky Way, than we had before. And so we have Cepheids we have a more reliable distance scale. However, this gives you again an appreciation for how difficult it is to actually build a three-dimensional universe out of that dark sky above us. Now, once Hubble discovers one galaxy is outside, he immediately goes on and measures the distances to many others because you can find Cepheid variables now that you know what you're looking for, and now you can just look at the nebulae, and Hubble comes up with a classification scheme. Another contribution of Hubble's is the classification scheme for galaxies by their apparent shape, and it has this tuning fork shape. So to the left are elliptical galaxies in order of increasing ellipticity. So some galaxies are ellipsoids, and Hubble is measuring how eccentric the ellipsoid looks to us. Of course, this is a crazy classification because it tells you nothing about a galaxy, because if you take a football and look at it head on, you can't distinguish it from a sphere. And so this, the E kind of classification tells you about the shape of the galaxy as it appears to us, but not much about the actual shape of the galaxy. And then there's this branching off into spirals with sort of increasingly intricate spiral arm structure on the one hand, and barred spirals on the other hand. And so the Milky Way, we now know recently, is a barred spiral. The Milky Way is an SBB type barred spiral. Andromeda, which has no bar, is an SB spiral galaxy. Later, other kinds of sort of less organized spirals were added by others, and a class for the degree of coherence of the spiral arms was introduced. So I can give a more precise classification, and we'll talk about the properties of various kinds of galaxies as we go on, now that we know they exist.